Okay. This, believe it or not, is, I believe, the 11th week. So it's moving along pretty quick. The next few chapters are pretty quick, small, I should say, not too many slides. So we'll be getting to those fairly soon. And I did mention we're probably going to end up with one or two live study sessions, meaning that we'll be done with all the lectures, and those days I'll be here. Good time to come in for question and answers. So, basically your time. So we'll see how it goes. We may have some, we may not. We'll see how it goes. Any questions? No? All right, well, let me continue with the slide that we ended up on, and that is on slide number 9. We are talking about moles, okay? And moles is a unit that we use in chemistry / physics, and it's basically nothing more than a number, and it just happens to have a very large number, 6.02 times 10 to the 23rd units, okay? Now, we talked about how to calculate the molar mass, because we know that the atomic weights of all the atoms, each atom has a specific atomic weight, that is that decimal number underneath the symbol. And the units for the atomic weight are grams per mole, okay? Now, to calculate the molar mass, we did some examples where we add up all the atoms that contribute to the molecule, and we tally up the number of hydrogens, carbons, etc., and the total weight that each one brought due to the atomic weight, and that adds up to the molar mass, also with the units of grams per mole. And like with any ratio, I can't over advocate, we can write that ratio as either, in this case, grams per mole or moles per gram. Which one we need is dependent on the units that we need to utilize, okay? So now we're going to calculate, we're going to go from grams to moles. And guess what? We can also go from moles to grams, okay? And so let's do a first example. First example, it says, let me get my pen here. How many grams are in 1.667 moles of oxygen gas, okay? All right, so this is what we're looking for, how many grams. This is what we're given, 1.66 moles of oxygen gas, the key word gas. So that tells us that we have to write the formula for example, for oxygen gas. And the fact that it gave you gas tells us that it's diatomic. It's one of the 7 diatomic elements. Now we need the molar mass. So call it MM of oxygen gas. There's 2 oxygens. Each one brings in 16 grams per mole. So we have a total of 32 grams per mole. We can write it like that, or we can write it like 1 mole of O2 over 32 grams, okay? And think about that ratio. That ratio is telling you that if you weigh out 32 grams of oxygen, you have 1 mole, okay? And if I have 1 mole, I have 6.02 times 10 to the 23rd molecules of oxygen. No different than someone said, I got a dozen eggs. What does that tell you? I got 12, okay? And here it just happens to be a very large number. Molecules of O2. All right, so we set the problem up like we've been doing, like we've been working through it. So we write down what we are given, and that is 1.667 moles of O2, okay? Obviously, we're going to need a conversion factor, so I set up my ratio here. And with respect to what I'm looking for grams of O2, okay? So that means, well, which one do I need? The 32 grams per mole, or the 1 mole per 32 grams? Well, what you're looking for in the problem tells you what you're setting up. If I set this up properly, I need moles in the denominator because I want moles to cancel out. And I want grams in the numerator, okay? Because that is what I'm looking for, grams of oxygen. Therefore, that just stands to reason that I want this one with the 32 in the numerator and the 1 in the denominator, okay? So notice how we set the problem up. We write down what we're given. We write down the units that we are needing, and then we plug in the conversion factors, the ratios, such that we set it up so their units cancel properly, leaving us with the units that we need to use. And so now it's a matter of just plugging those values into the calculator and looking and given the number here, okay? All right, so we don't forget sig figs, remember that. Sig figs started from way back in the early chapters, and it's gone through the whole semester, and it will continue. We always keep track of the sig figs. Atomic weights, molar mass, they're not a factor. Exact numbers are not a factor. What we're given is 1.667 moles. Well, that is a measurement. It came from grams. Okay. And somebody out there measured 53.34 grams of oxygen, and that represents 1.667 moles. Okay. So that is 4 sig figs. Our answer should have 4 sig figs. Okay. Notice again, keeping track of your units, moles cancel, leaving us with grams. And so another thing here to notice, if you haven't, is when I have moles, in general way to look at this, I multiply by the molar mass to give me the units of grams. Okay, I have moles, I want to go to grams, I multiply by the molar mass. So what does that infer? That the opposite is, that if I have grams and I want to get to moles, guess what? I'm going to divide by the molar mass. Okay, so moles to grams, I multiply. Grams to moles, I divide by the molar mass. All right, here's another one. Here we're asked to calculate the number of moles if you have 45 grams of silver. Okay. So silver, we're going to need to look up the atomic weight of silver, because we're going from moles to, we're going from grams to moles. Okay. And so periodic table tells me that the atomic weight of silver is 107.87 grams. All right. And so if I forget, oops, what happened here? If I forget how to set that up, again, write down what I'm given, grams of silver. You are looking for moles of silver. Therefore, my conversion factor will have grams in the denominator, moles on top, okay? Because my grams cancel. And so you can see that I'm dividing by the atomic weight of silver when I start with grams. And that gives me 0.42 moles. Now, remember that I stated when we start doing calculations with respect to reactions, we can't go from grams to grams. We have to take the grams of one reactant, convert it to moles, and then relate that mole to the other reactant. And that what comes into play there is that balanced chemical equation, because once we know the moles of whatever we want, a compound A, we know how many moles of, say, compound B in the reactant is going to be needed because of that stoichiometric relationship between the reactants that came from balancing the reactions, okay? But we have to start off with moles. Once we got moles, we can go into other places. We can't go directly grams to grams. We have to go through moles. That part I can't overemphasize because occasionally students want to go directly from grams to grams, and we can't do that. The only way you can do that is this, and from going directly from grams to grams, okay? And I want you to think about this for a second. If I have a very general reaction, I'm just going to tell you A plus B equals, it reacts to give us C and D. All right, if I started off with 10 grams of A and I was able to isolate my products and I end up with, let's say, I don't know, 20 grams of C and 10 grams of D, can anybody tell me, based on this information, how many grams of B did I start off with? Anybody want to give that a shot?
20.
20, exactly. Now, how do we know it's 20? Because conservation of matter and mass, right? So we got a total of 30 grams over here as reactants. I need to end up with 30 grams of products. And so I got, I got 4 variables. I'm always going to have, if I'm given this type of problem, I need all the other variables. If I'm looking for one variable, I need what the other variables are. And that's great. However, we generally, when we're doing calculations, it's not that simple. I wish it was. We ended up with, we don't know what C and D is. We don't know what their amounts is, but we know what one reactant is, okay? And you might be asked the question, based on that one reactant, calculate how many grams of C I need, okay? And so the relationship is between A and C. And the only way I can do that, because I don't know how many grams of this B I have or this, and I can't do what I just did earlier, but I can do it by converting everybody to moles. If I start off with 10 grams of A, I convert A into moles. From moles, I can go directly to moles of C, and from C, I can go into the grams, okay? And this concept of the moles, that's why it's important. That is our common factor. And I'm doing it from A to C, but I could easily have done that between A and B, okay? Or A and D, or B and C, or even between C and D. And that is why, remember when I said, look at all the ratios after you balance the equation, look at the reactants, and then the reactant ratio was whatever it was, and then look at the products and look at that ratio, and even the products have their own ratio between them, because that ratio is going to allow us to go from moles of one reactant into the moles of the other product, okay? So this step here that we're doing is quite important in that figuring out how to convert our grams into moles, because that's going to push us into being able to calculate other things. All right, so here we got this, here we have this one. We have grams. If I had 0.055 moles of water, how many grams does that represent is the question. And so I have 0.0554 moles of H2O. Obviously, I need a conversion factor, and I need to get to grams of H2O. Therefore, I need grams in the denominator. Oh, excuse me. Wake up, Fred. Moles. Let me erase that. I need moles in the denominator and grams in the numerator because my moles will cancel. Well, this factor, grams over moles, molar mass. So I got to go back up here. I'm given water. I got to write that its name into formula, and that is, as we hopefully know by now, H2O. Okay, once that, we got to calculate the contribution for two hydrogens and the contribution for the oxygen, and we end up with a molar mass, mm, of 18.02 grams per mole. Never forget the units, grams per mole. Now that we have the molar mass, we plug it in here with 18 in the numerator and 1 mole in the denominator. And now you simply can do the math. And hopefully you should come up with the following answer, okay? 0.998 grams, you know? Think about that. That's how small it is. Almost 1 gram gives you 0.055 moles of water molecules. And keep in mind, you know, now you might think, well, wait a minute, what does that correspond to actually molecules of water? We can calculate that, can we not? Yeah, I can take the 0.554 moles of water, and you might want to do that as an exercise, and multiply that by Avogadro's number, and that's molecules here, because we're working with molecules, but it could have been bananas if we were working with bananas, okay? And 1 mole. And even with that small amount of water, almost 1 gram, you can see that you have a ton of water molecules in that 1 gram, almost 1 gram of water. Okay, almost 1/18 of a mole, right? Because we know that the molar mass of water is 18 grams. We're calculating here about almost 1 gram, so it's about 1/18 of a mole. And so it's a small amount, mole-wise, small amount volume-wise, but a ton of actual molecules. All right, so here we have this one where we're being asked to calculate, if you start off with atoms of, let's say, potassium, okay, you want to know how many grams that consists of. All right, so we are starting off with atoms, 4.75 times 10 to the 16 atoms of potassium. And eventually I may or may not need the molar mass or atomic weight, but I just put it down there anyway because I just might need it, you know. I put it down just out of habit, go calculate it and or look it up if it's just an atom. And potassium has an atomic weight of 39.10 grams per mole. Now, some people have asked me, well, why do you say one time atomic weight and another time you say molar mass? Okay, well, the difference is this. When I say atomic weight, I'm just talking about one atom. We're just talking about the element. When I talk about molar mass, we're talking about a compound. And a compound, as you know, by definition, has more than one atom involved. Okay, so that's the difference. Okay, so I got the atomic weight ready. I know Avogadro's number. I know that Avogadro is 6.02 times 10 to the 23rd atoms, bananas, apples, oranges, whatever, per 1 mole. In this case, I put atoms because that's what we're working with, atoms. Okay. And so I can't go directly from atoms to grams because, again, I need to get that conversion factor. I'm working within potassium, yes, I know, but even when working within one element, I need the common factor, which is the mole. So I got to convert atoms into moles. And so I need a conversion factor, which obviously will be Avogadro's number. And I need atoms in the denominator. okay, and 1 mole in the numerator because I want atoms to cancel. And so I can plug that in, 6.02 times 10 to the 23rd, 1 atom. So if I stop the calculation at this point right here, I converted the number of atoms into the number of moles of potassium. But I got to take it one more step because the question is asking me to convert to grams. So I need grams on the numerator and moles in the denominator. Notice my moles cancel for potassium, and that's where the atomic weight comes into play for potassium. And so now I set that up properly. I double check my units, okay? Making sure that my units cancel out properly. I got atoms canceling here. I got moles canceling here, leaving me with grams of potassium, which is what the problem asked for. So you notice I started with atoms. I needed to get to grams. I needed first to convert that atoms into moles. So from that point, I can now go into grams, okay, within the element. Or I could have gone in, once I'm in moles, I can go into moles into another element, another reactant. All right, so now you got it all set up, and now it's up to you to plug the number in. All right, remember the buttons for scientific notation, either EXP or E or X10 to the X power on your calculator. If you have any trouble with that, we can definitely talk about how to set that up in your calculator. All right, so finally you end up with 3.9 times 10 to the negative 6 grams of potassium. Yeah, give this some thought. Look how small that mass is, that weight. 3.09 times 10 to the negative 6. Move that decimal point over 6 times, okay? And you're looking at what we got, 1, 2, 3, 4, 5, and 6 grams. That's a small quantity, right? Most balances in the labs couldn't weigh that with that accuracy, okay? Because they probably weigh up to maybe the best in a typical lab is about 4 decimal places. I mean, you can get balances that weigh more, but a lot more expensive. You wouldn't be in a general chemistry class. For us, it's probably 3 to 4 decimal places. And then look at this number here. Look how humongous that number is. That represents how many individual atoms of potassium there are. It is a humongous number. But all of them combined, the total weight is 3.09 times 10 to the negative 6 grams. Extremely tiny. Again, to give you the perspective of the size of the atoms we're talking about. They're extremely, extremely tiny. All right, so any questions about converting from grams to moles? Grams to moles, we're dividing by the atomic weight or molar mass to get from grams to moles, and vice versa when we went and go from moles to grams. Okay, then. So this brings us to what is called a molar volume. Now, when we were talking about physical properties of solids, liquids, and gases, solids and liquids, we have a very specific physical property as far as their volume is concerned. We can actually calculate the volume for solids and liquids. However, for gases at the time, we said, no, they don't have a fixed volume. Okay, so we kind of lied to you a little bit. They do have a fixed volume, however, only under special conditions. And we call those conditions STP, which stands for standard temperature and pressure. Okay, well, standard temperature is 0 degrees Celsius. 0 degrees Celsius. And standard atmosphere is what we call 1 atmosphere. That is the atmospheric pressure of where we're at now. We're approximately 1 atmosphere, and that does change depending on the weather and also depending on the altitude that you live. The atmospheric pressure in, say, Colorado up there in Denver is a little bit different, say, than, say, down here in Arizona and Phoenix, which is slightly different, say, if you're closer to the ocean, okay? All right, but under those conditions of 1 atmosphere and at 0 degrees Celsius, a gas has a molar volume of 22.4 liters. Every mole of gas at STP has a volume of 22.4 liters. Okay, guess what? That's another ratio. 22.4 liters per mole. Think about this. Now, if we're given conditions of STP, we can go from volume to moles. Earlier, we went from grams. So we go to the balance, we weigh it out. There's some things we can't weigh out, okay? Like a gas, it's a little bit difficult to weigh out. More challenging. Not that it's not impossible, it's just more challenging. However, we can measure volume, okay? And at STP, we know that in that 22.4 liters, any gas, 1 mole, that is equal to 1 mole, which means there's 6.02 times 10 to the 23rd molecules of gas at STP. So if we look at specific examples of the gas they're talking about, any gas, it's hydrogen, fluorine, ammonia gas, xenon, and methane. All of them have 1 mole, okay? And all of them have the same number of molecules. Just like we have a mole of solid, we have 6.02 times 10 to the 23rd. We got a dozen, like the dozen represents 12 for 1 dozen, 1 mole represents 6.02 times 10 to the 23rd. I realize I may sound redundant, and I'm doing that for a reason, because this concept sometimes is challenging for first time you've been exposed to it, okay? All right, so if you forget what that mole represents, just think of a dozen. What that dozen represents is a number, just 12. Now, obviously, every gas here has a different molar mass. Hydrogen, H2, 2 hydrogen atoms. Fluorine has a different molar mass because we're dealing with different elements, okay? Just like we talked about small, medium eggs. A dozen small eggs are going to weigh much less than a dozen medium eggs, which weigh much less than a dozen ostrich eggs, okay? Yes, we all got 12. And they all have a different weight. The same is true here. What they all have in common, and only at STP. So if you're given a problem about trying to calculate volume of a gas, and they don't mention STP, the letters STP, or they may give you the temperatures. If they don't give you any one of these 2 things, you cannot calculate anything. And it just, the answer is, can't calculate it, don't have enough information, okay? But only at STP, all those gases occupy a volume of 22.4 liters. Bear in mind, 22.4 liters is a measurement, okay? It's a measurement, and therefore, as with all measurements, there's a degree of uncertainty. Therefore, this factor could be the 22.4, could affect the number of sig figs in your calculations, okay? Atomic weights, nope, okay? Only any exact numbers, nope. Only numbers that are measured quantities, okay? Measured quantities. And 22.4 liters is a measured quantity. All right, let me clear this up a little bit. So how do we use it? Okay, well, before I begin, just a repeat of what I just mentioned, 22.4 liters per mole for any gas at STP, okay, which is at 0 degrees Celsius, which is freezing actually, okay, and freezing point of water, and 1 atmosphere. So how do we use it? Well, you can see on top that we have the relationship of 22.4 liters written either with liters in the numerator or liters in the denominator. Any ratio we're working with, you can do that. And so we set up this problem like we've been doing all problems. Okay, it's a different type of problem, but no problem, right? We break it down, write down what we're given, identify what we're looking for. So what is the volume? That is what we're looking for. Okay, what are we given? We're given 1.25 moles of argon gas. Okay. And guess what? This is important. We are at STP. So we can utilize the 22.4 liter per mole relationship. So let's write down what we got. Okay, we got 1.25 moles of argon. Okay, obviously we're going to have a conversion factor here. All right. And now you might say, like, what is argon? 39 point, make sure I get it right, 39.95 grams per mole. Okay, some people would say, all right, you mentioned write down the atomic weight of the argon gas. All right, I did that. It's just out of habit. I got it down there. But ask yourself, do I really need it? Because nowhere in the problem is the question, anywhere in the problem, there's a question being asked that deals with grams. See that? Because the atomic weight and the molar mass deal with grams per mole. Nobody here, but go ahead and write it down in case you need it. So let's go back to the problem. We are in moles, and we're looking for the volume, which obviously is going to be liters of argon gas. Another thing to think about, look at the number you're given, 1.25, okay? Earlier I said 1 mole, 22.4 liters. So you're about 1.25 moles. So that would suggest that your number should be a little bit bigger than the 22.4, does that? Because you got a little bit more material. Let's find out. All right, so we set up, we got moles. We want moles in the denominator, cancel that out. And we want liters in the numerator, okay? And so we're gonna use the one on the left where we got 22.4 over 1 liter. So our numbers definitely is going to be greater than 22.4 liters. It's definitely. Why? Because we're multiplying by 1.25. All right. And so let's plug that number in. And sure enough, you calculate 28.0 liters of gas, which is consistent with the fact that you're given 1.25, which is greater than 1 mole. All right, of argon gas. Okay, next one. Similar scenario. All right, we can go ahead and put 32 grams per mole, molar mass, just in case we need it. But let's look at the problem. How many moles is 30.4 liters of oxygen gas at STP? All right, so think about this problem here. I got 30.4 liters, 30.4 liters. Definitely much bigger than 22.4, right? Which suggests that our number is going to be greater than 1 mole, greater than 1, okay? Because you got 30.4 liters. All right, so let's put down what we have. 30.4 liters of O2. And we're looking for moles of O2. Okay, so liters in the denominator, moles in the numerator. Okay, so we got 1 and divided by 22.4. You can see liters cancel out. We're good to go. we're taking 30.4 divided by 22.4. Our number definitely is going to be greater than 1. Okay. And it is almost 1.4. Okay, 1.36 moles, which is consistent with the numbers we're given and the mathematics we did. Okay. All right. And I say that for a reason, because, you know, sometimes if you inadvertently plug that number in and you, let's say you got, let's say you did, instead of dividing, you multiply. Well, that gives you about 681 liters. If your answer was roughly, come on. If your answer was 601, I think it was 600, double check. Yeah, 681 is what I meant. If it was 681 liters, that should bring up a big old flag. Okay, big flag. Because that number is definitely inconsistent with the mathematics you're doing here. So that's because you're looking at 30.4 liters. You know that at STP, that's just a little bit above 22.4. So your answer should be a little bit over 1. But if you're getting 681, that suggests that you inverted that ratio and you multiply by 22.4 and not divide by 22.4. Okay, but it's important that you look at the answer and say, does that make sense? Does that make mathematical sense? All right. This one here, couple of things to look out for. What is the mass? Okay, so they're asking you already, well, how many grams of 4.50 liters of chlorine gas at STP? Okay, so we're still at STP. We can still use the 22.4 liter per mole relationship. All right, but we need to first, let's write down what we're given, 4.50 liters of chlorine gas. Obviously, we're going to need chlorine gas is what, 35.4. So we're looking at what, 70 some grams per mole. I'm gonna round it up for right now. I'll get the exact number in a second. Okay, so it's just 35.4 times 2. Why? Because chlorine gas, remember, is Cl2 diatomic. So it's 35.45 times 2, approximately 70 some grams per mole. I'll show you the exact one in a minute. And what are we looking for? We're looking for mass. So we're looking for grams of chlorine. All right, so if we're at STP and we have liters, well, I gotta get, just like we did to the previous example, we need to get to moles, all right? And so I need liters down here and moles up here. So that is that one, 1 over 22.4. So that cancels my liters, and at this point, I'm in moles of chlorine gas, which is where I want to be. And so, where am I at? Oh, 70. Let me write that down, back it up. And so here, I need to get rid of moles. So moles are down in the denominator and grams are up the top. And so that 70.9, that is the molar mass of chlorine gas over 1 mole. My moles cancel, leaving me with grams of chlorine gas. So let me clear the mess up and I'll bring back the answer. You can see that 4.5 liters, 4.50 liters at STP of liters of chlorine gas would weigh 14.2 grams, 14.2 grams, okay? So we took the volume of a gas that we know, and we calculated how many grams that will consist of. That's what we did here. So this flow chart, and we're going to give you another flow chart down the road that's going to add more information, but this is the start of the flow chart with respect to calculations of going from one unit to another unit, okay? And notice that the center unit around everything is moles. You got to go through moles to get to any place on this, unless you're in moles already, moles to moles, you can do that, no problem. But if you start off in grams, you need the molar mass, okay? And guess what? You are dividing by the molar mass to get to moles if you start off in grams. Now, once you're in moles, you can go one or two ways. If the question asks for atoms, ions, molecules, for units, bananas, oranges, pickles, whatever, you got to multiply by Avogadro's numbers when you're at moles to get to that unit of whatever you're measuring. And if you are at STP and only at STP, only, that's important. Only at STP can I go down in this direction, and I can use that relationship of 22.4 liters per mole. So multiplying that by 22.4 gives you the volume of that gas at STP. Keeping in mind that this is a measurement and that 22.4 represents 3 sig figs. So depending on the number of sig figs in your calculations, the 22.4 liters can affect the final sig figs, okay? Keep an eye out for it, that, because there are some questions like that you may be kind of stumped and say, oh, wait a minute, I kept track of my sig figs. And my answer is, yes, you did. However, you did not keep track of 22.4 liter. All right, so that is the flow chart to get you from point A to point B. Everything's going through moles, okay? And you're going to see the other flow chart, which we're going to utilize quite a bit. So let's do an example here. The question, for example, says, how many grams does 17.35 liters of neon gas mass or weigh at STP? Okay, so we write down what we're given, 17.35 liters, and we're looking for units. I unfortunately gave you the answer there, but the answers should be 15.6. More importantly, the units should be grams of neon. So that's what we're looking for unit-wise. And so I set up my conversion factors such that as I check them through, as I put them up, then I can see that my liters cancel, my moles cancel, leaving me with the units of grams, telling me I am in the right track. And notice here, 17.35, it's a measurement, it's 4 sig figs, but our answer has 3 sig figs. Why? Because the 22.4 liter is also a measurement. Even though it's a conversion factor, it is a measurement. Therefore, it could be a factor in determining the number of sig figs. And in this example, it was. So our answer is 15.6 grams per liter. Okay. Once we know that, the next question is this: well, how many atoms does this represent? So here we go again. We start off with 17.35 liters, and then this time we put units. In this case, units of atoms. And again, the answer is there. So that means that I'm looking for atoms. That means that I need to use Avogadro's number someplace, right? So step number 1, I need to convert the first set right here, I need to convert that to moles. The volume needs to be converted to moles, and that's why, since we are at STP, I can use that relationship. Once I'm in moles, I use Avogadro's number with 6.02 times 10 to the 23rd on top. My moles cancel, leaving me with the units of atoms, which is what I'm searching for. Okay, that could have said bananas for all you, know. So that's what we're looking for. So you plug in the number, and you should come up with 4.66 times 10 to the 23rd atoms. All right, that's pretty big number. It really is. All right, and then you ask yourself, does that number look reasonable? Well, let's think it through. Okay, we starting off with 17.25 liters, knowing that in 1 mole it's 22.4 liters. So obviously the 17.35 is smaller than the 22.4. So that suggests that my final answer should have less than should be less than 6.02 times 10 to the 23rd, excuse me. And it is. It is smaller than Avogadro's number because we have a smaller volume to work with in the beginning. Okay. Okay, good. Any questions? Don't hesitate to stop me. No? All right. We had talked about density before, and density, again, another ratio with respect to, it is a ratio of mass over volume. Okay. And normally we would weigh the material and determine the volume either directly or indirectly by displacement, if that's a solid, for example. And then we just plug the numbers in and boom, there we go, we got the density. With respect to gases in STP, we can just simply utilize, we don't really have to measure anything, because we know that at STP, the molar mass, or the 1 mole gas is equal to 22.4. So we can do the following. If we look at this molar mass, which is grams per mole, divided by the molar volume, okay, which is 22.4 liters per mole. Okay, I'm dividing by a fraction, am I not? Okay, and so this is X. I don't know what molar mass should be. Whatever X is the gas, but I'm just looking at the units. So when I, for example, I'm going to take 1/3 and I divide it by 1/4. Do I not take the 1/4 and invert it? Yeah. So 1/3 becomes 4/1. So my answer is 4/3. Right. Same thing here with the units. Grams over mole becomes moles. Well, I'm going to say X grams. Moles divided by 22.4 liters. That means my moles cancel, and look at the units that I had left over. X grams, whatever the molar mass it is, divided by 22.4 liters. Unit wise, grams per volume. Density, grams per volume, which gives me the density of a gas at STP. Again, STP. Clear this up. Let's plug it in. All right, so plug that in. So ammonia, we just need to find the molar mass of that gas, and we know how to do that now, right? We just add up the contribution of all the atoms in ammonia. We got 1 nitrogen at 14, 3 hydrogens at 1.01 for each one. That gives us a molar mass of 13.4 grams per mole. Dividing that by 22.4 tells us we have a density for ammonia at STP of 0.761 grams per liter. Now, you might say, what about the sig figs? Well, as I stated, we don't use the molar mass because they come from, infinite sig figs. But again, the 22.4 liter is a measurement. So regardless of what this guy is over here, the 22.4 liter, the 3 sig figs will govern how many sig figs your answer will have. Okay. Earlier, in calculating the molar mass, I did mention this, but we're gonna talk about it a little more detail. It's called the percent composition. You already know how to calculate the molar mass, right? We add up all the atoms involved in the compound. Now, what we do is real straightforward. Let's to figure out the molar mass of, what are we looking at here? Water. Okay, this is the molar mass of H2O, which was 18.02 grams per mole. Okay, we have 2 hydrogens, 1 oxygen. Now what we do is we take the individual contribution of each atom and we divide it by the total molar mass. So you can see we had 2 hydrogens that brought in 2.02, and we divided by the total molar mass of the molecule, in this case water, which is 18.02, and we multiply by 100, and guess what? We get a percentage, right? So hydrogen represents 11.2% in the molecule, the structure of water, H2O. We do the same with oxygen. Oxygen brought in 16.0 grams for the oxygen. There's a total of 18.09 multiplied by 100. So oxygen represents 88.79% of the percent in the molecule of water. Okay. Now the question here is like, oh my goodness, sig figs can be a little bit of a challenge because we're working with atomic masses, right? We're talking molar mass. My suggestion, the final answer that you get up, just to be consistent, and just keep it with 2 sig figs, because each of the molar masses that we provide has, let me restate that. Keep 2 decimal places, not sig figs. Each of the molar masses that we provide in the periodic table have at least 2 decimal places. So for percent composition, keep the answer with 2 decimal places. Because in reality, you wouldn't be wrong, since each one here represents an infinite number of decimal places. Your answer could have an infinite number of percentage, but keep it at 2 decimal places, only for this, okay? Only for this type of calculation. Now, once you're done with that, all your percentages should add up to 100%. And that is consistent with a water molecule anywhere wherever we find it. If we do an analysis of it, it would consist of roughly 11% hydrogen and roughly 89% oxygen, okay? Now we can do this with any compound you are given. For example, find the composition for TNT. Anybody know what TNT might stand for? Trinitrotoluene. Okay. It's quite of a hazardous chemical to work with. It does tend to be heat sensitive, it's shock sensitive, and it goes through allowable. Trivia question, side note. Anybody know by chance who invented this? Who invented TNT? There's a very famous prize that's awarded every year in different fields, not just science, but literature, peace. That sound familiar? Nobel. Yeah, Nobel's work, Nobel was a chemist and he was the one who synthesized TNT, which is quite impressive because to make it is quite challenging and quite dangerous. Anyway, they give you the formula and there's 7 carbons, 5 hydrogens, 3 nitrogens, and a total of 6 oxygens, okay? And recall that exercise we did before where we were giving you a formula and just asking you how many atoms you have of each, and you end up with a total number of atoms, okay? Well, now we're back here again. We're getting you ready to get to this point here so you can identify how many of each atoms we have. Now you know the atomic weight. You can add up the molar mass, okay? All right, so well, again, we use the Chem 130 for atomic weights. And we got 7 carbons, each at 12.01, that is 84.01 grams per mole. 5 hydrogens at 1.01 each, that's 5.05. We have 3 nitrogens at 14.01, that gives you a total of 42.01. 6 oxygen at 16 each. That is a total of 96.00. So the molar mass for TNT by nitrotoluene is 227.15 grams per mole. Okay. Now to figure out the percent composition, we take the individual atom total amount and divide it by the molar mass. So we take 84.05 for all the carbons divided by 22.7 times 227.15 and multiply by 100. Okay, that corresponds to 37.01%. Do the same for hydrogen. Okay, that's 22.2%. Nitrogen comes up to be 18.5%. And finally, oxygen at 42.26%. And that should tally up to 100%. All right. So here's an example where it said just keep it with 2 sig figs when you're just working with atomic masses. Because again, they have an infinite number of sig figs, and just to be consistent and not as ambiguous, keep it at 2 decimal places, regardless as how many other digits you have. 2 decimal places. All right, well, try these at home, okay? We have, how many liters will 3.425 grams of carbon dioxide gas occupy at STP? Work it through, and let's see if you end up with 1.74 liters, okay? Second question is how many molecules are in 3.425 grams of carbon dioxide? Okay, and so here we're going to need at least 2 conversion factors because you start off with grams. Remember, you need to go to moles. So you're going to need the molar mass of carbon dioxide. Okay, so you're going to need to figure out its formula and then figure out its molar mass. And then from that information, that gives you 2 moles of carbon dioxide. Then you need Avogadro's number to get you 2 molecules of carbon dioxide. And see if you can come up with 4.68 times 10 to the 23rd molecules. Okay. In this example, again, you're still working with carbon dioxide, so go ahead and calculate. You don't have to calculate the molar mass because you did that for the first one. So if you're given 3.0 times 10 to the 15 molecules of carbon dioxide, how much would that weigh is the question. And so that's a pretty large number of molecules, right? 3.0 times 10 to 15, large number. But you should have a weight of 2.2 times 10 to the negative 7 grams. Extremely tiny, tiny, tiny. All right. that brings us to the end of chapter 12. Now, what I want to do is not continue with 13. 13 is just as small. I'm going to give you time to digest this chapter. So unless you got some questions, we can go over questions. We'll just stop it here. And maybe use you're on your own to use those other D's to figure that out. Okay. And if you still have challenges with that or don't quite understand these three, bring it in Thursday and we'll go over it and make sure you calculate it correctly. Okay. All right. Any questions?